In this video, we're going to go through the sensory or afferent division of the peripheral nervous system. So previously we went through the motor division, that's the fight or flight, rest and digest, autonomic nervous system. This unit, or this lecture, will go through the sensory division, so visceral and somatic sensory. So sensory information is going to the brain. A few different types of sensory information. So somatic sensation is somaesthetic, so skin, or proprioceptive. Proprioceptive is like if you shut your eyes and I tell you to lift your arms in front of you, you would be able to do that, kind of knowing where your body is in space. Visceral sensation is information about your internal organs that we call viscera. Special senses, vision, hearing, taste, and smell. So, in order to have sensation, we need two things. We need a stimulus, and then we need receptors that are able to respond to the stimulus. They will then change the stimulus into electricity, which is called transduction. Here's a list of the different types of receptors you guys should be familiar with. Notice the root words here are correlated with what they are. So photo means light. That's a receptor that checks light. Okay, I'm not going to read these all for you, but you should be able to recognize them. So information about the stimulus that can be communicated, so things that you're able to be aware of. The modality, so the type of stimulus. Is it a taste? Is it a sensation? Is it pain? What is it? The location, so where is it? How strong it is, how much pain it is, how cold it is, and then how long it lasts, the duration. We can classify receptors based on one of three ways. So by modality, the ones you guys saw earlier, different receptors. The origin of stimuli, so proprioceptors sense movement and position of your body, or by distribution, so where they are in the body. So special senses are only in your head. General senses are throughout the rest of the body. So the receptors that you have are able to adapt to the situation that they're in. So we call this receptor adaptation. So this is a little bit different from habituation, but it ends up with the same result. So if you remember, habituation was in the central nervous system. That's your brain decreasing its kind of response to the stimuli. In receptor adaptation, this is happening at the level of the receptor, not at the level of the brain. So two main types of receptors. Tonic receptors, which don't really adapt, and if they do, it's going to be really slow. These don't adapt because, for example, they're telling you your arm is lifted straight in front of you. You need to have constant information telling you that so that you know where your arm is. You can't just get used to that because then how would you know where your arm is? Phasic receptors adapt rapidly. These maybe, for example, could be like pain. Okay. So an example of a rapidly adapting receptor is the Pacinian corpuscle. If you remember way back to the first unit, looks like this, wrapped around a little sensor here that senses pressure, vibration. These adapt very quickly. So for example, if you lay down and you put your blanket over you, right away that pressure you're able to sense, but after it's there for like a couple seconds, you don't really notice that pressure anymore. So something called the receptive field is really important. This is the region where a receptor is sensitive. So how great or small of an area a receptor is able to receive stimuli. Discrimination also really important, is your ability to tell the difference between two different stimuli. So if you look at this picture here, you can see two different stimuli, two little pokey things. I forget what these things are called. But two different pokes are happening. Here, there are two different receptors with different neurons. So this signals to your brain as two pokes. On the right-hand side, the one in pink, these two pokes both end up going to the same neuron, and they both go to the brain, and you only perceive one poke. So this is called discrimination, the ability to tell the difference between two stimuli. So there is higher discrimination here on the left. Discrimination is enhanced by higher receptor density. So regions of the body that have more receptors in a smaller space, like your lips, have better discrimination. And then lateral inhibition also enhances discrimination, and I'll go through what that is in a second. So here, the receptive field is the area that the receptor is able to be stimulated. On the top, all of this goes to one neuron. This is a large receptive field. On the bottom, there are three different fields going to three different neurons. So these are smaller receptive fields. Which one do you think has higher discrimination, top or bottom? Hopefully you're thinking bottom. If you're able to poke on number 1 and number 3, you'll feel those as two separate pokes, versus if you poke anywhere along here, it's all going to be perceived the same. So poor discrimination on the top and better discrimination here on the bottom. So areas of the body that have more receptors need more processing power in the central nervous system to integrate all of that information. Which regions of the central nervous system devote more space to those parts of the body with better discrimination? So if you guys remember those weird looking pictures of the guy that was really disproportionate, so that's the sensory homonucleus. The somatosensory cortex within the central nervous system is what that was showing, remember. Here's another picture showing discrimination. You can see this coming in as one stimulus versus these two little pokes are showing two different stimuli. So lateral inhibition is pertaining to the neurons on either side of the stimulus. So here there's a little pencil poking the skin. The neuron that's right underneath that is going to be stimulated, and the neurons on either side of that are going to be inhibited. That allows us to have increased sensitivity and increased discrimination. This inhibition occurs in the central nervous system. So this is a result of the interneurons in your brain. So here you can see this needle is poking a part of the skin here with this one neuron. So we're stimulating the one neuron, and then the two on either side are being inhibited. This picture, if you stare at the black dot, something is supposed to happen. I can't remember what. It doesn't seem to work for me. But this one, if you guys play it on your PowerPoint, you'll see that there's a little missing dot that starts to kind of travel around, and after a while it starts to turn green, and that's because of lateral inhibition. So we'll finish up this video talking about different nerve endings, and then we'll talk about pain a little bit. So two main types of nerve endings: unencapsulated nerve endings and encapsulated nerve endings. So unencapsulated just means that the dendrites at the end of the neuron are not covered with connective tissue. They are free. So free nerve endings that sense temperature and pain. Merkel discs in your skin sense light touch. And hair receptors wrapped around your follicle are able to sense your hair movement. Encapsulated nerves, you can see here they all have some type of connective tissue wrapped around them. Meissner corpuscles we went through, these are light touch and texture. Pacinian corpuscles are deeper. They're sensing vibration, pressure, and stretch. And then Ruffini corpuscles are a little bit deeper, and they sense heavy touch, pressure, and they also are in the joints to sense joint movement. So pain is really important. It signals us that there's damage happening. And then it also motivates us to do something to make the pain stop. The receptors for pain are called nociceptors, and they notice tissue damage. These are free nerve endings. They are not encapsulated. Pain is transmitted in one of two different types of nerve fibers. You guys are familiar with A fibers and C fibers. A fibers are really fast. This is like your sharp stabbing pain. C fibers, slow. This is like your burning pain. Clinically, it's really important to know which type of pain an individual is having because certain medications are useful or not for each different type of nerve pain. So pain can be controlled through the spinal cord, and pain is signaled via this neurotransmitter, substance P. Referred pain is your body's kind of inability to tell us exactly where the pain is happening from your internal organs. So for example, a heart attack, you guys have probably heard, oh, you might have pain in your chest, the left side of your chest, down the left side of your arm, maybe even in the jaw or potentially even on the back. So obviously the heart isn't on your left arm, but the pain signals and the nerves send that information to your skin or muscle, and then you perceive it as muscle pain. Another example, individuals with like kidney pain might feel like they just sprained a muscle in their back or something. They're not really sure why they're having this back pain, but actually it's their kidney pain. So this referred pain is kind of just our body's inability to really be specific about its internal organs. Your body's able to control pain. So we have our own pain suppression system within our body. So we release opiates onto the afferent pain fibers. We're able to create our own opiates, so we call them endogenous. They are created within our body. These control pain. Exogenous opiates are created outside of the body, and they can be administered as a medication to control pain. Okay, we will pick up with special senses on the next video.